Hello everyone, my name is Ali, and I will be presenting Linformer self-attention with linear complexity. This is a really important baseline for my research, and I will explain it in a really simple manner. So let me start by explaining the difference between feed-forward neural networks, convolutional neural networks, and transformers. So imagine we have 5 input tokens and 5 output tokens. How do we route information between these tokens? In feed-forward neural networks, we connect everything to everything. Means we connect every node to every other nodes, and then we learn the weights of the connections. In convolutional neural networks, however, we connect each token to only its immediate neighbors. That means we basically look at the local regions of the image. How about transformers? In transformers, we transform one sequence into another, and we do that by calculating the dot product between the keys and queries. So imagine we have an incoming information, and then we calculate the dot product between the keys and queries. So as you can see, these two vectors have high cosine similarity. As a result, they will have a high dot product. So this incoming information will most probably will be routed through this token. And the same goes for these two. So imagine we have an input length, a sequence length of n. So in order to do these dot products between keys and queries, we need n squared operations. And if we consider the embedding dimension of each vector is d, we will have the query matrix n by d, the key transpose matrix d by n, and the dot product between them is query key transpose, which will be an n by n matrix. So in modern transformers, this sequence length, it's usually 512. And this inner dimension, the embedding dimension, will also be of the same order of magnitude. So as a result, the dot product, the query key transpose, will almost have a rank of 512. But this is not actually how the modern transformers work. So in modern transformers, we have multi-head attention. That means we're going to split this inner dimension into multiple lower dimensional vectors. For example, in this case, each of 128. And then those lower dimensional vectors will perform the self-attention. So what this does, so we no longer have an n by d matrix, right? We have an n by d over 4 dimensions. And for K transpose, we also have a d over 4 by n. But this doesn't really change the final dimension of the matrix, right? It will also be n by n, 412 by 412. But we are actually reducing the embedding dimension, right? So that means the new matrix will have a new ranks of almost 128. So this is actually what this paper exploits, and they claim this is low rank. So Linformer, self-attention with linear complexity. So they say that the standard self-attention mechanism of the transformer is of order of n squared, but in this paper, the self-attention mechanism can be approximated by a low-rank matrix, and then it reduces the overall self-attention complexity from order of n squared to order of n, and while matching the performance, it's much more memory and time efficient. So what is the attention mechanism? So as you know, in the attention mechanism, we have queries and with their corresponding weights, we have keys with the weights, and we also have the values, the actual information that we want to route. So we calculate the dot product between the queries and the keys, right? Query key transpose with their weights, and then we scale them appropriately, and then we run them through the softmax. So what this paper claims is that this matrix over here, this resultant matrix, is low rank. We can call it matrix A. But is this matrix P actually Lorentz after running through softmax? So they will answer that by claiming that self-attention is Lorentz. So they made an empirical investigation into Roberto. Roberto is just a model based on BERT. And they ran it into with two public datasets, Wiki 103 and IMDb. So they calculate the eigenvalues of that matrix P I showed, and they kind of um, experience a really interesting result. As you can see here, in the eigenvalue index of 128, there's sort of a kink, right? And as you can see in the right side, as we go deeper into the layers, right, as the layer index is increasing, the values are higher. That means the network is actually putting more and more information, more and more important information, right, into lower, into fewer and fewer layers, right? So as we go deeper into um, the network, right, the network puts more and more information into fewer and fewer dimension in this routing. So they propose a theorem that self-attention is actually Lorentz. So we have queries, keys, and values, which are of the dimension of n by d, and then we have their corresponding weights, dimension d cross d. And we also have the values, right, with their corresponding weights. So they say for any queries, keys, and values, there exists a Lorentz matrix P tilde, which is n by n. And for that P tilde, this equation right here holds. And they actually claim that that P tilde is actually Lorentz. And as you can see here, the rank of P tilde is log of n. So what this equation here actually means. So this right here is just a distance, right? So, and this right here is the projected norm of P, the basically the original matrix P. And we have an error coefficient as well. And this P tilde here is the routing matrix, the approximation of P, right? And the omega transpose is the information we want to route. And P is just the original routing matrix. So what they actually, and they claim that this happens, that this distance being lower than the projected norm of P, it happens with high probability, this PR and over here, it happens with high probability that most of the time, um, this distance will be lower than the projected norm of P. So what this means is that if we use P tilde, they claim there exists a Lorentz matrix P tilde, right? That if we use that P tilde, that projection matrix, that routing matrix, to route the information we want to route, right? It will not be too much far away when we use the original matrix to route the same information, right? So that means P tilde is actually a really good approximation of the original matrix P, right? Because of that, the distance um, is so close, and this happens with high probability. So this is their first theorem. How they prove this, how they prove that there exists a Lorentz matrix P tilde, they use a theorem, a lemma, Johnson-Linde-Strauss lemma, or JL. So what JL proposes is that imagine we have data in a higher dimensional space, in this case a three-dimensional space, and then we want to project it using phi, a projection matrix, into a lower dimensional space, in this case a 2D space. So what JL does is that it routes the information using this projection matrix, but the data, the distance between the data will be almost preserved. That means the information will not be too much distorted if we use a good projection matrix. And this is what they actually claim. So the model um, is a really famous model. Um, so we have the keys, and then we project the keys values, we project it. We have the queries. We calculate the scale dot product attention, query k transpose, and then we run it through a softmax function, and then we use that softmax to route the values, the actual information. So as you can see here, what they do is that we have a matrix over here, which is n by d, right? So we use a projection matrix, which is k by n, not anymore n by n. We use this projection matrix to project this matrix, and as a result, so we project the keys using this matrix, right? So this is a key matrix, and we define a matrix which is k by n, not n by n anymore, because we wanna reduce the rank from n squared to kn, right? And if we use this kn, right, and then we multiply it by this key matrix and then their corresponding weight, we will have a resultant matrix of k by d instead of n by d. That means we are actually reducing the sequence lengths from n to k. So conceptually speaking, if we have the same 5 input tokens and 5 output tokens, now instead of routing these 5 tokens to 5 tokens, we can route these 5 tokens to only 2 tokens, right? And then we calculate their corresponding keys and query vectors, and then we only route these 2 to these 5, right? We only calculate the dot products of these 2 key vectors with this 5 query vectors. That so if we consider these two are k, right? Instead of having order of n squared, which is routing these 5 into 5, n by n and a squared, we now only need to route k by n. That means the new order will be of order nk instead of n squared. That means it's linear, right? Using John Strauss lemma, we successfully made it linear. So they build this in this fashion right here. So before the attention mechanism was between the queries and the keys, right? Now they have added a projection matrix E that project the keys into a lower dimensional sequence such that this will result in an n by k matrix over here, right? So we don't need to route n by n things, right? We just need to route n by k things. And we also need to down project the values, right? Um, because we are routing the actual information, the values as well. So we need to down project it as well. So we do this by similar matrix F, which reduces the dimension to k by d instead of n by d. And basically, if we multiply these two, n by k and k by d, the final matrix will be again of dimension n cross d, but we are reducing the computations a lot, right? Because it is low rank. How they define this projection matrices E and F? They define it like this: E is sigma times R, and F they basically E to minus sigma times R, where R is basically um, independently and identically distributed entries from this, and sigma is just a constant like this. So, and as far as I understand, these values are not learned anymore. So these matrices are not learned. The second theorem they claim is that the self-attention is actually linear. So again, for any queries, keys, and values and their corresponding weights, they say if we define k like this, there exist those E and F projection matrices, right, that this equation right here holds again. So this is sort of its same equation that if we use the projection matrices E and F, right, in compared to when not using them, the distance will be so close. That means the data will be not far away from the original data. So if we route the data, if we route the information using E and F matrices, we will not be far away when we route the information using the original P matrix, right? The original routing matrix. So that means this again, this E and F will be a good approximation of the P matrix, the original P matrix. So they proved this again by distributional Johnson-Linus-Raus lemma, which I explained. They performed some experiments on Linformer, and as you can see here, they are comparing it with the standard transformer with sequence length of 512. So as we know, standard transformers complexity is n squared, right? But here, Linformer uses n by k. The order is linear, n by k, right? And they perform the experiment on different k's, k64, 128, and 256. And as you can see, Linformer is actually matching the performance of the standard transformer, although it uses the complexity of Linformer is actually linear, right? But it is matching the performance of the standard transformer, and that is really good. And that's it, everyone. Thank you for your attention and hope you enjoyed.